All right, welcome back everyone to the deep dive. We've got a really cool one today. We're heading out into the depths of space to explore a brand new discovery that's kind of shaking things up in the astronomy world.
That's right.
It's called ASKAP J1839-0756.
Yeah.
Now, I know, a mouthful, right? But trust me, the object itself is way more interesting than its name, and that's why we're doing this deep dive, to break down exactly why this discovery is so significant and what it might be telling us about the universe. And we'll be looking at a few different sources. Some are all about the discovery itself. Some dive into the basics of pulsars and neutron stars. We're going to figure out what makes this thing tick.
Yep. It's a real head-scratcher, that's for sure. Basically, we're dealing with a cosmic object that's making us rethink what we know about pulsars. Kind of like if you discovered a creature that walked on water, you'd have to re-examine everything you thought you knew about, biology. And that's what we're going to do today, break down this cosmic puzzle piece by piece so everyone listening can follow along.
Perfect. So to set the stage here, let's start with some Astronomy 101. What are we talking about when we say neutron stars and pulsars? Can you give us a crash course?
Sure. So picture a star way bigger than our sun. Way, way bigger. Now, when these massive stars reach the end of their lives, they don't just fade away quietly. They explode in a supernova. That's like the grand finale, a huge cosmic fireworks show.
Yeah. I mean, we're talking about explosions that can outshine entire galaxies, right?
Absolutely. It's an insane amount of energy. And what's left after all that? Well, sometimes the core of that star, what's left of it, it gets crushed under its own gravity. All that matter gets squeezed into this tiny, super dense ball. And that, my friend, is a neutron star.
I remember hearing somewhere that like a teaspoonful of neutron star material would weigh like billions of tons. Is that even possible?
Yeah, it's wild, isn't it? We're talking about density that's just incomprehensible. And that brings us to pulsars. Now, not every neutron star is a pulsar, but all pulsars are neutron stars. What makes them special is they have these super strong magnetic fields, and those fields, they channel beams of radio waves that shoot out from the star's poles, like beams from a lighthouse.
Ah, the lighthouse analogy. I was wondering when that was going to come up.
Right. So these neutron stars, they're not just sitting there, they're spinning. And often they spin ridiculously fast. As they spin, those beams of radio waves sweep past us. So if one of those beams happens to point towards Earth, we see it as a pulse of radio waves, hence the name pulsar. It's like the lighthouse beam sweeping past, giving us a flash each time.
It's amazing how regular those pulses can be. It's almost like a cosmic clock ticking away.
Yeah.
So most pulsars are spinning crazy fast, right?
Yeah, exactly. We're talking many, many rotations per second in most cases, like a cosmic blender on high speed.
Which brings us to our star of the show, ASKAP J1839-0756, and why it's turning heads. Maybe I shouldn't say star because it's not really like any star we've seen before. This thing's more like a cosmic slowpoke compared to those super spinners.
Yeah, for sure. This is where things get really weird. So this ASKAP J1839-0756 was discovered by the ASKAP telescope in Western Australia. And the thing that makes it so strange is that it rotates incredibly slowly.
Like how slowly?
It spins just once every 6.5 hours.
Well,
Most pulsars do thousands of rotations in that time. It's literally the slowest pulsar or, cosmic lighthouse had ever recorded.
It's a total outlier then.
Totally. I mean, how do they even pick up on something rotating that slowly? Wouldn't the signal be like super faint and easy to miss?
Well, that's what makes this discovery even more incredible. They basically stumbled upon it during a routine sky survey. Just scanning the skies, and this thing pops up. It wasn't like they were looking for it. It wasn't even on their radar. And what they saw initially, it was just this single burst of radio waves that faded really quickly, like 95% dimmer in just 15 minutes. It was like it blinked at us and then disappeared.
So it was kind of like a cosmic fluke. They even caught it.
Right. And because they only saw that one burst, they didn't immediately think, oh, this is periodic, something that repeats regularly.
Gotcha. So what happened? How did they figure out that it wasn't just some random cosmic burp? Well, they got curious. They needed more data, so they followed up with more observations, not just with ASKAP, but with other telescopes too, like the Australia Telescope Compact Array and the Meerkat Telescope down in South Africa. And that's how they confirmed that these weird bursts they were repeating every 6.5 hours like clockwork.
Clockwork's a funny way to describe it, given how slow it is.
It's true. But the point is, those follow-up observations, they nailed down that incredibly slow rotation period. It was like solving a puzzle.
Okay, so we've got a pulsar that's spinning at a snail's pace,
Right.
which is already bizarre enough. But there's more to this story, right? Our sources mentioned something about it pulsing from both ends.
That's right. It gets even weirder. Here's the thing. With most pulsars, the axis they spin around and the axis of their magnetic field, they're pretty much lined up. It's like our lighthouse analogy again. The beam of light points in a certain direction, and as the lighthouse spins, we see that beam. But with ASKAP J1839-0756, things are tilted.
Oh, I see. So it's not a perfect alignment.
Nope. Not at all. It's like the lighthouse is wonky, so instead of just seeing one beam sweep past, we're actually seeing beams from both magnetic poles as it rotates.
Oh, that's wild. It's like it has two lighthouses going at once.
Yeah, and that's not common at all. Astronomers call these fainter pulses that happen between the main pulses interpulses, and they only show up in a small percentage of known pulsars, like maybe 3%. It's like catching a glimpse of the lighthouse keeper walking around inside the lighthouse while the main beam is still spinning. It gives us this extra information about the pulsar's geometry, its shape, and its magnetic field.
So not only is this thing rotating super slow, but it's also giving us this double pulse show.
Exactly. And it's the first time we've ever seen this double pulsing in an object that rotates this slowly. It's like finding a tortoise that can do backflips.
A backflipping tortoise. That's a great image. But this has got to be causing some serious headaches for the scientists trying to figure this thing out. It's like it's breaking the rules of how pulsars are supposed to work, right?
Totally. It throws a real wrench into our understanding of how these objects work. The whole idea behind how pulsars emit those radio beams, it relies on them converting rotational energy into electromagnetic radiation. Like a spinning top, as they slow down, they lose energy.
Okay, so the faster they spin, the more energy they have to power those radio beams.
Right. And the current thinking is that once a neutron star spins slower than a certain rate, like around 1 rotation per minute, it just doesn't have enough juice to power those radio emissions anymore.
And this one's doing it at 1 rotation every 6.5 hours.
Exactly. So it's like way, way below that theoretical limit. Like imagine a car running out of gas and then somehow still driving down the road. It doesn't make sense.
It really doesn't.
One of our sources even says flat out, according to what we know about neutron stars, ASKAP J1839-0756 shouldn't even exist.
Ooh, strong words. So if it shouldn't exist, what are some of the ideas being tossed around to explain it? Are there any loopholes in the theory, or maybe some other way it could be doing its thing?
Yeah, there are some really interesting theories out there. One of the leading ones is that maybe ASKAP J1839-0756 isn't just any neutron star. Maybe it's a magnetar.
Magnetar. What's that?
So magnetars are like neutron stars on steroids. They have these insanely powerful magnetic fields, trillions of times stronger than Earth's magnetic field. I mean, it's mind-boggling.
That's a seriously strong magnet. So how would that explain the radio pulses we're seeing?
Well, the thinking is that magnetars might generate radio waves a different way than regular pulsars. Instead of relying on their rotation, they could be tapping into the energy stored in those super strong magnetic fields. It's like they have this backup generator that keeps the lights on even when the main engine is sputtering.
Okay, I can kind of see how that could work. But are there other magnetars out there that are spinning this slowly?
That's a good question, and it's where things get tricky again. Most known magnetars, they spin much faster than ASKAP J1839-0756, like seconds instead of hours. But there is one very interesting exception, a magnetar called 1E161348 array 5055. And get this, it has a rotation period of almost 6.5 hours. Super close to our slowpoke.
So there's precedent for a super slow magnetar.
Kind of. The catch is, this magnetar, it only emits X-rays, not radio waves. So it's another example of an ultra-slow rotator, but it doesn't quite match the radio profile of ASKAP J1839-0756. It's like close, but no cigar.
So it doesn't totally fit.
Right.
What else are scientists considering? I think I remember reading something about white dwarfs being thrown into the mix.
Yep, another possibility is that this might not be a neutron star at all, but a white dwarf. White dwarfs are what's left over when a smaller star, not as massive as the ones that form neutron stars when they reach the end of their lives. They're not as dense as neutron stars, and they tend to spin much slower.
Okay, so that would explain the whole slow rotation thing, but how would a white dwarf be sending out these radio pulses?
That's the big problem with the white dwarf idea. We've never seen an isolated white dwarf emitting radio pulses like ASKAP J1839-0756. And astronomers have looked, they've tried to find any sign of a white dwarf where this radio source is, using different kinds of telescopes, looking for different wavelengths of light, but so far, nothing.
So it's an idea, but there's no evidence for it.
Right.
So basically, ASKAP J1839-0756 is like this cosmic riddle wrapped in a mystery, right?
Right.
And it's forcing scientists to really re-examine what they thought they knew about some pretty fundamental astrophysics. What's your take on this whole discovery? What's the big takeaway for you?
I think what makes this discovery so important is that it's really making us question our understanding of neutron stars. How they work, how they evolve, what makes them tick. And it's showing us that our current theories, well, they might not be the whole picture. There might be stuff going on that we just haven't even considered yet.
So the universe is showing us we still have a lot to learn.
Exactly. It's a reminder that we don't have all the answers. And the fact that we're able to detect these incredibly faint signals from something so far away, it's amazing. It shows just how far our technology has come.
Yeah, it blows my mind every time I think about it. Our instruments are getting so good, we can pick up these faint whispers from across the universe. It's pretty awesome.
Absolutely. Our sources make a great point about this. It's like the universe is this giant playground full of surprises. We think we know the rules, and then something like this comes along and throws everything out the window. It's a good reminder to stay curious and keep exploring.
It makes you wonder if something like this can come along and shatter our assumptions about neutron stars. What else might be out there waiting to be discovered? What other rules are just waiting to be broken?
That's the beauty of science. It's all about discovery. This ASKAP J1839-0756, it's a reminder that the universe is full of mysteries and things we don't understand yet. It's a reminder that we need to keep asking questions, keep pushing the boundaries of what we know, and always be ready for the universe to throw us a curveball.
So for everyone listening, we've basically just scratched the surface of this incredible discovery. We've got this cosmic object that's acting totally out of line, spitting out radio waves while spinning way slower than it should, and even flashing at us from both poles. And our current science can't fully explain it. And that's okay. That's what makes it so exciting.
Right. And it's a reminder that even when things seem impossible, even when something shouldn't even exist, there's always more to learn. The universe is vast and complex, and there are still so many secrets out there waiting to be uncovered. Who knows what other mind-blowing discoveries are just around the corner?
I guess we'll just have to wait and see.
Exactly.
Till next time.
See